Alright, this is Pat Brown here. I am a graduate student at San Jose State University in the Department of Meteorology and Climate Science. And so I am just going to give some introductory videos here on climate science, and hopefully that will help people understand the issue a little bit better. Alright, so this first video is going to be on the Earth's energy balance and the greenhouse effect. So two very important issues when we're talking about the kind of current concerns about climate change and fossil fuel burning. So the first question that I want to ask here is, what would cause the temperature of the Earth to change? And when I say temperature of the Earth, I'm talking about the entire Earth's surface temperature kind of averaged all together. So just one value for the temperature of the Earth. So you can see from a map like this is annual mean temperature, that of course, you know, the tropics are warmer than the poles, and higher elevations are cooler than lower elevations. So there's a lot of variation, from place to place. But we're just going to say that we're talking about all of this averaged together to get kind of one temperature for the entire surface of the Earth. So the first law of thermodynamics says that the temperature of really anything just comes down to energy in versus energy out. There is an important caveat there that's assuming that no work is being done on the system or by the system, but as long as we can assume that no work is being done on the system, which is definitely true for the Earth, then it all comes down to just energy in versus energy out. It's a balance. And so if energy in equals energy out, then you have no change in energy in the system, and so you have no change in temperature. You have constant temperature over time. And this makes sense because temperature is just a measure of energy. So if you have the same amount of energy coming in as is going out, then you have no net change in energy, and so then you wouldn't see temperature change because temperature is a measure of energy. So you get a change in temperature when you have an imbalance. So in the case of warming, you would have a situation where energy in is larger than energy out. So basically energy is accumulating in the system, and again, this could be anything. It doesn't have to be the Earth, but it's definitely the case for the Earth as well, that if energy is accumulating in the system, then you will see that manifested in an increase in temperature, because temperature is a measure of energy. So then the other scenario would be cooling, where energy in is less than energy out, so you have a net, negative flow of energy, or the system is losing energy, so you would see that manifested in a cooling in temperature. So when we talk about the Earth system in particular, we have to kind of understand what type of energy we're talking about here. So the type of energy is electromagnetic radiation. So we're all familiar with a lot of different types of electromagnetic radiation: X-rays, ultraviolet rays, infrared rays, light, the visible spectrum, microwaves, radio waves. So all these things are just different types of electromagnetic radiation. And the only thing that's different about these different types is their wavelength, that some have longer wavelengths and some have shorter wavelengths. And so when it comes to the situation that we're talking about with the Earth here, energy in comes from the sun, so this is electromagnetic radiation from the sun, and energy out comes from the Earth. And so there's a very important difference between the energy that comes in from the sun and the energy that goes out by the Earth, and that is expressed in Wiens Law. And so what Wiens Law says is that warmer objects emit more of their radiation at shorter wavelengths than cooler objects do. So the sun is a lot hotter than the Earth, and so the sun emits much more of its radiation at short wavelengths, and the Earth emits much more of its radiation at long wavelengths. So this horizontal axis here is just wavelength, where to the right the wavelength is longer, and to the left the wavelength is shorter. And so you can see that there's just an important divide between the sun and the Earth in terms of what type of radiation they emit. So the sun emits a lot of radiation at short wavelengths that we can actually see, and the Earth emits radiation at longer wavelengths that we often call infrared wavelengths or heat radiation. And those are wavelengths that we can't see. Our eyes are not tuned to see those such long wavelengths, just like we can't see radio waves and other longer wavelengths of radiation. So if you just consider the Earth without an atmosphere, you can kind of set up an energy balance, and you can calculate pretty easily how much energy should be coming in and then how much energy should be going out. And with that information, you should be able to figure out the temperature. And so if you do that and you don't consider any atmosphere on the Earth, what you get for a temperature of the surface of the Earth is 0 degrees Fahrenheit. And so immediately something is wrong with that, because we know that the average surface temperature of the Earth is 59 degrees Fahrenheit. So this is much cooler than the observed temperature of the Earth. So this means that, okay, if we don't consider the atmosphere and we get something that's much cooler than reality, then maybe the atmosphere has some property that causes the Earth's temperature to be warmer than it would be otherwise. And so this is the exact situation that Joseph Fourier was considering in 1824. He had done this calculation to figure out what the temperature of the Earth should be without an atmosphere, or he didn't account for the atmosphere, and he calculated that the temperature would be around 0 degrees Fahrenheit, so way cooler than what we actually observe. So he was the first person to actually propose that the atmosphere has an effect on the Earth's temperature. So what he proposed is what we now call the greenhouse effect, and basically what that is that there's a property of the atmosphere that allows energy in, so it allows shortwave energy to come into the system, but it partially blocks the outgoing energy. So the way that it could possibly do this, and that's why it was important to go over the shortwave versus longwave, is that some gases in the atmosphere would have to be relatively transparent to shortwave radiation, so they would let it in, but they'd have to be relatively opaque to longwave radiation, so they would let less longwave radiation out. So that would tip the scale in the energy balance diagram, so that energy in would remain the same, but energy out would get smaller, and so you would get a warmer surface than you would have otherwise. And so he was the first person to propose this in 1824. And then in 1859, John Tyndall actually discovered that he was right. So John Tyndall was the first person to look at the properties of various gases and how they interacted with different wavelengths of radiation. And what he found, using advanced technology for the day, what he found is that different gases absorb and emit radiation at different wavelengths. So this is a graph showing wavelength on the horizontal axis and absorbance on the vertical axis. And so these 5 gases here are 5 very important greenhouse gases, we call them. And greenhouse gases, what makes them greenhouse gases is that they interact with long wave radiation that the Earth gives off. And so you can see that they all interact with different wavelengths of radiation differently. But what they all have in common is that they all absorb some wavelengths of radiation that the Earth is giving off, but they don't interact very much with the shortwave radiation that the sun is the sun is emitting towards the planet. So these gases are water vapor, methane, carbon dioxide, nitrous oxide, and ozone. And actually these gases make up just a very small percentage of the atmosphere overall. But because of this effect where they absorb the long wave radiation coming off the surface of the Earth, it makes them very, very important for the temperature of the planet overall. So here is just a summary diagram of the radiation budget or radiation balance of the Earth. So on the left hand side here we have energy coming in from the sun. This is shortwave energy on the left. And on the right hand side we have energy going out. And you can see that energy is leaving the surface of the atmosphere. And so all these units, by the way, are just watts per meter squared. So this is just flow of energy, because a watt is a joule per second, and so then we're just dividing a joule, which is a unit of energy, by time, and then by unit of surface area. But so, I mean, they're just flows of energy around. So this is showing that we have a certain amount of radiation coming from the surface, and then it gets kind of absorbed and re-emitted by these greenhouse gases here. And so the greenhouse gases absorb it, and then they turn it around, and this component is what causes the Earth's surface to be warmer than it would be otherwise, and it often gets called back radiation. And so it's these gases that we were looking at over here this water vapor and methane and carbon dioxide, nitrous oxide, and ozone that are absorbing the long wave radiation coming off of the surface of the Earth and then emitting it back towards the surface of the Earth, which causes the surface to be warmer than it would be otherwise. A quick note on this: this is not actually how a greenhouse works. So it's too bad that the greenhouse effect is called what it is, because that's really a misnomer. A greenhouse actually works by physically trapping hot air close to the surface, where normally hot air would want to rise, and the greenhouse traps the hot air close to the surface. But anyway, if we look at this diagram, we can kind of try to figure out what's going on in terms of the temperature of the Earth, at least with these numbers. So if we look at energy in versus energy out, we can figure out, is it warming or cooling or constant? And so let's look. So first, energy coming in, we have 342 watts per meter squared of shortwave solar energy coming in. But we see that some of that, a portion of that, gets reflected both by clouds and by the surface. So that actually doesn't really count as energy in, this 107. So to get the energy in, you'd really have to take the 342 and subtract the 107. And so what you get when you do that is 235 watts per meter squared. And then if we look at the energy out, so the long wave portion over here, energy out, we see that a certain amount is emitted by the surface, and then greenhouse gases absorb some of it and re-emit it back towards the surface. But eventually what leaves is 235 watts per meter squared. So that's the same. So energy in this case, equals energy out. So the way this diagram is set up, we have a balance and we have constant temperature. But the concern these days is that humans are burning fossil fuels, and it's very easy to demonstrate that humans burning fossil fuels have increased greenhouse gases in the atmosphere. So when we increase greenhouse gases in the atmosphere, we make it harder for the Earth to emit energy to space. So effectively what that does is it decreases energy out in our energy balance. So we didn't increase energy in. What we did is we decreased energy out to get this in balance, and that will cause warming. That will cause energy to accumulate inside the Earth's system, and that would be manifested in an increase in temperature, because temperature is just a measure of energy. So this kind of may seem a little bit confusing, but it should be pretty intuitive, because we actually do this quite a bit in our day-to-day lives, whenever we put on clothes, actually. So here is a skier who has some heavy winter jackets and snow pants on, and really the point of putting this stuff on is to warm yourself up by inhibiting energy out. So unless it's like an electric jacket or something, you're not actually increasing energy in. What you're doing is you're making yourself warmer by making energy out smaller. You're decreasing your body's ability to radiate energy to your environment. And so this makes sense that as we've seen greenhouse gases increase over time, this is just looking at CO2 concentration, as we've seen the increase in greenhouse gases like CO2 over time, we have seen an increase in temperature. And of course, they don't correlate perfectly, because there's a lot more things going on in the climate than just CO2. But in the long run, the more greenhouse gases you have in the atmosphere, the smaller the energy out term gets, and so the higher the temperature should get in the long run. And so that is kind of why the temperature should change, why the Earth's temperature should change, and so it really has to do with the energy balance and the Earth's greenhouse effect.